So the first thing that I just want to mention to you guys is the fact that when it comes to trig, there's really only 5 types of questions you can be asked. All right, and this comes like at the end of grade 12, so in your finals. The first type of question that you can be asked is to simplify an expression, and we're going to do the first 4 types today. This is going to involve your use of reduction formula, co-ratios, identities, pretty much all of your basic trig knowledge you are going to have to apply and simplify in an expression. And that is also true when it comes to proving a trig identity. You're going to have to use the knowledge you have from the basics of trig in order to do that. So that's the second type of question, proving a trig identity. Third type of question is using a diagram on the Cartesian plane. This is really, really important because often what we do is we forget to draw the diagram and then we make our lives hard. Okay, there's no reason to make your life hard. Once you have a diagram, things are actually a lot easier. We will do more of these as we start with the grade 12 stuff. But that's the third type of question. Fourth type of question is solving a trig equation. So this is that general solution stuff with the plus k times 360. And then there's problem solving questions. Now, guys, I'm going to focus on the first 4. Problem solving questions, like I say, that is up to you to go and revise because it often deals with a 2D trig. So when I say 2D trig, I mean area rule, sine rule, cos rule. You need to go and revise that. Unfortunately, we just don't have time. It's also not the bulk of the trig. These other 4 questions are. Same as trig functions. That is for you to revise. We just don't have the time. But trig functions really are not super, super tricky. They don't really increase in complexity when it comes to grade 12. Okay, so there's a couple of things I want us to remember before we get started with the stuff. So the first thing that I want you to remember is that trig is working with angles and side ratios in right angle triangles. So you've got 3 basic trig ratios that you need to know: sine theta, cos theta, tan theta. Sine is opposite over hypotenuse. So in this triangle, if this is theta, the side opposite is AB. And the hypotenuse is always opposite the right angle, so AC. Cos is adjacent over hypotenuse. So adjacent is the side right next to your angle. So this would be BC over the hypotenuse, which we already know is AC. And tan is opposite over adjacent, which is then AB over BC. So these trig ratios you need to know and you need to be able to work with. Now, I remember these trig ratios with SOHCAHTOA. I don't know how many of you learned it like that. There's SOHCAHTOA. Sine is opposite over hypotenuse. Cos is adjacent over hypotenuse. Tan is opposite over adjacent. So that's how I remember my trig ratios. If you have another way to do it, obviously, that's absolutely fine as long as you remember them. I don't really care. But the next thing that you need to remember is what happens to your ratios on your Cartesian plane. So you've got 4 quadrants on your Cartesian plane. I'm not too sure why I've chosen 1, 2, 3, 4, because generally we actually use Roman numerals for our quadrants. So I made a choice here, but it doesn't really matter. In the first quadrant, you are working with acute angles. So this is where all of your ratios, sine, cos, and tan, all of them are positive. So this is just your basic theta, nothing strange there. When we start moving into quadrants 2, 3, and 4, we start being able to apply reduction formula. So in quadrant 2, only sine ratios are positive, and this is where the reduction formula of 180 minus theta exists, because it's less than 90 but less than 180, greater than 90 but less than 180. Quadrant 3 is now where all your tan ratios are positive. This is now the reduction formula 180 plus theta. And then when we move into quadrant 4, this is where only cos is positive, and this is a reduction of 360 minus theta. So those in green that I put there are your reductions. Now, obviously, there's co-ratios and stuff like that, which I'm going to write down for you guys now as well, because they are really important to know. But honestly, if you can apply your reductions, you are probably 70 to 80% of the way there. Co-ratios, they come up, but not as often as the reduction. So these are really, really important to know. Right, if we are going to talk about co-ratios, the really important ones that you need to know are the 90 plus or minus co-ratios, which I'm going to write down for you guys now. Right, so 90 minus theta. If we just think about where this is in quadrant 1. 90 minus theta is quadrant 1. This is where everything is positive. So if you've got sine 90 minus theta, the co-ratio says that the name changes to cos, and you're working then with just the angle of theta. Now it's going to be positive because everything in quadrant 1 is positive. So cos 90 minus theta is equal to name change sine of the angle theta. So that's 90 minus. You also get 90 plus. So 90 plus theta. This is now in quadrant 2. So now we need to be careful, because if we've got sine of 90 plus theta, in quadrant 2, sine is positive. So it's just a name change to cos theta. However, if we had cos of 90 plus, cos is negative in quadrant 2. So the name change is negative sine theta. So you always look back to what the original ratio was. Because the original was cos, it means that it's a negative. So the 90 plus and 90 minus co-ratios, those are the really important ones. Okay, you do also get 270 co-ratios, which I'm going to write down for you, but honestly, guys, avoid them if you can. There's other ways to do it, so I would just avoid them. If we do look at the 270s quickly, just for your own interest and in case you want to know, we get 270 minus theta. So 270 minus is now quadrant 3. Quadrant 3 is where only tan is positive. So what that means is that sine of 270 minus theta is going to be a negative cos theta. And for cos of 270 minus theta, we're going to get negative sine theta. If we now look at the 270 plus theta, this is then quadrant 4, so only cos is positive there. So sine of 270 plus theta is going to be negative cos, because sine is negative in quadrant 4. And cos of 270 plus theta, cos is positive in quadrant 4, so it's positive sine theta. So like I say, my advice, don't stress about the 270s. You can work around them. You don't really have to use the 270s. I'll be honest, I don't use the 270s. There's always another way to do it. So I wouldn't focus on them. I would definitely know my 90 plus or minus co-ratios, those you do use. But the 270s, I really wouldn't stress. But they're there for you. You have them if you want to apply them. Right, so I'm just going to stop here in case you want to screenshot all of this information. And again, grade 12s, if you have a question, you need to ask me. I'm not really even going to stop to breathe. So you just need to let me know when you have a question, what the question is, and I'll help you. Okay. All right. So if we look at our first type of question, which is simplifying a trig expression, this is now where you are going to have to be able to apply a bunch of different things. The really important things for you to be able to work with are your reduction formula. So 180 plus minus 360 minus. So reduction formula are important. Your co-ratios are important. And sometimes, not like hugely, your trig identities are also important. I don't know why this is happening with my pen. We're just accepting it because it's been wild tonight. So we're just going with it. So these are the 3 things you need to be able to work with: reduction formula, co-ratios, trig identities. So we have been given negative cos of 180 minus x times sine of 90 plus x minus 1 divided by tan squared 540 plus x times sine of 90 plus x times cos of negative x. Right, so all of this stuff we're going to have to deal with as we move along in this reduction, in this trig expression. Now, grade 12s, you do it step by step. So you look at the first factor, you deal with it. You move on to the second factor, etc., etc. So my first factor is this one over here, this negative cos of 180 minus x. Now remember that negative in front here is a -1. So I'm just going to write it as -1 for now. Cos of 180 minus. So think about your cos diagram and think about where 180 minus is. 180 minus is quadrant 2, and that's where only sign is positive. So cos of 180 minus x is actually a negative cos x. And we'll deal with signs and multiplication in a second. Then I move on to my next factor. So my next factor is sine of 90 plus x. That is a co-ratio. 90 plus x. You can go back to your list if you want to. The 90 plus gives me cos x. Because 90 plus quadrant 2, sine is positive. So sine of 90 plus x, positive cos x. And then we've got that -1 at the end, which we can deal with. It's a separate term. We'll deal with it later. All right, so now I just want to take a little detour here, because this is one that we often make a mistake with because of that squared. So tan squared 540 plus x. Whenever you have a squared ratio, what I need you to remember is that you're actually working with tan of the angle, so tan of 540 plus x, and that ratio is being squared. So that's how I like to write squares. And the reason for that is, if this tan ends up being a negative ratio, a negative value squared is actually a positive. And so where we often trip up is we make a mess of the signs. So if you put it in brackets like this with the squared right outside and you figure out the ratio first, it makes life easier. Okay, the next thing that you need to remember is the fact that this 540 is more than a revolution. But you can add or subtract 360 degrees as many times as you want to an angle. It doesn't change anything. So if you, let's say, have an angle somewhere in quadrant 1, if you add 360 degrees, you end up in the same point. If you were to subtract 360 degrees, you would end up in exactly the same point. So adding or subtracting 360 degrees doesn't change the value of what you're working with. And so what it allows you to do is it allows you to get an angle that is in the first quadrant. So if I subtract 360 degrees from this, I get tan of 180 plus x, all being squared. 180 plus is quadrant 3. That's where tan is positive. So I'm working with tan of x squared. And so I have tan squared x. That whole bottom 540 plus x nonsense, tan squared, blah, 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 actually just simplifies to tan squared x. And so it's really important that we do understand what those squares are telling us. So that's the first denominator factor. Sine 90 plus we've already done. We know it's cos x. And now we've got cos of a negative angle. Okay, so if we go back to our beautiful Cartesian plane drawing here, actually, I'm just going to draw a new one. Negative angles are when we measure an angle from the x-axis clockwise. So these are negative angles. It means we're working in quadrant 4. Now, what that means is that if we have cos of a negative angle, because cos is positive in quadrant 4, we're actually just working with cos of that angle. However, when it comes to sine of a negative angle and tan of a negative angle, because both of those are negative in quadrant 4, you are then working with negative sine of the angle and negative tan of the angle. So those are negative angles that we learned about in grade 11. Because this is cos of a negative angle, it means that I'm just working with positive cos of that angle, and now I can start to simplify. So back in my numerator, -1 times negative cos is actually just positive cos x times cos x. That's a lot of O's going on there. So let's try that again. -1 all over. Now, guys, the second you see tan, I would think about my identities. The reason for that is because cos and sine have a close relationship with each other. Cos and sine have the co-ratio relationship. They have got the, I don't know where I'm going with this. They've got the co-ratio relationship. There's that relationship. And so what we need to think about are our trig identities. Don't know why I chose that line again. So let's go here. Now, right now, as it stands, you know two identities. You know the tan identity, so tan theta is equal to sine theta over cos theta, and you know the squared of the Pythagoras identity. Sine squared theta plus cos squared theta is equal to 1. Now, these can be manipulated in any way. So, for example, this squared identity, you can isolate sine squared, and you can have sine squared theta is equal to 1 minus cos squared theta. You could isolate cos theta, or cos squared theta rather, and you would have 1 minus sine squared theta. You can manipulate these identities in any way that you want to isolate the trig ratio that you want. Now, this is going to be important because in my denominator, I've got a tan. Everything else is cos. So if I get this to be a tan and use my tan identity, at least I'm introducing a cos here, and I can actually start working with more like factors. So the tan squared x actually simplifies or can be changed to sine squared x over cos squared x. You then still have your times cos x times cos x, and cos x times cos x is cos squared x. So I'm going to write it as that. If I can simplify, let's simplify. In your numerator, cos x times cos x, as I've just said, is cos squared x minus 1. And in your denominator, when you now multiply these two things, so the fraction times cos squared x, the cos squared x's cancel. Okay, they cancel each other out. And so all you actually have in your denominator is sine squared x. Now, what I want you to take note of is the fact that this numerator looks very similar to this identity that we have over here. It's not the same because the identity is 1 minus cos squared x, whereas our numerator is cos squared x minus 1. But I can fix that. If I take a negative out, I end up with negative cos squared x plus 1 all over sine squared x. And if I rearrange those terms, I've got minus 1 minus cos squared x over sine squared x. Now, as we can see, this now matches up. Oh, just golly. This now matches up with my identity. So what that means is I can replace that whole bracket with a sine squared x. So minus sine squared x over sine squared x is equal to negative 1. And I have simplified that whole wonderful expression that I started off with to 1. Now, guys, again, I know this is a lot of information. I'm not under the impression that this is super easy either. I get that trig is a struggle for a lot of us. But if you can apply the basics, if you can go and say, okay, cool, I'm comfortable with my trig identities, my co-ratios, and my reduction formula, you go step by step. I didn't try and do everything at once. I worked with one factor at a time, and I simplified as I went along. Okay, you can't do everything at once because it's just going to get overwhelming. Go step by step, and then you will be able to simplify your expression. Right, so I'm going to stop here for you guys to take a screenshot because there's a lot of information on here. Obviously, if you have questions, please ask. Like I say, I am motoring. My grade 12s at school tell me I just run. That's my default setting. But again, it's because there is a fair amount of matric stuff that we need to get through. But we also need to make sure we understand the basics. Okay. Right, so guys, I'm just going to assume that if you don't unmute yourself, if you don't put something in the chat, you're good, you don't have questions. Right, so let's have a look at the second type of question in trig where you have to prove an identity. So this is proving or prove the following identity: 2 minus cos squared x times 2 plus tan squared x equals sine squared x. Okay, now there's something really important we have to remember. You do not work this as an equation. Okay, it is not an equation. You are trying to prove that the left is equal to the right, but you do not work with it as an equation. I don't know if someone sent a message on the chat, but your message is no longer there. don't know if you deleted it or something's happened, but if you did have a question, please just resend it because it's not there anymore. Right, so you do not work it as an equation. What you need to do is you need to pick a side to work on, and your goal is to manipulate it so that the left is equal to the right. That's your goal. Now, guys, when picking a side to work with, you pick the more complex side. Sorry, I just need a sip of water. So when I say you pick the more complex side, you pick the side with more stuff going on. On the left, I've got the 2 minus cos squared x times 2 plus tan squared x. But on the right-hand side, I just have sine squared x. That's a one single term situation. That's not the more complex side. The more complex side in this case is the left-hand side. And so this is the side that I'm going to manipulate in order to get it to equal sine squared x. Kristen, yes, we do carry on with lessons throughout the holidays. So I have said, but obviously things have been chaos. So yes, the lessons carry on throughout these short holidays. Over the longer June, July holiday, we will take a break. You guys also would have just written your first set of exams and you do need a break after that. So we take a break over that. But over these holidays, we do carry on, and I'm just carrying on with the Trig course. Okay, so it's, if I remember correctly, it's only 3 nights over the 2-week holiday that we have. So it's not a huge amount. And yes, we will have a lesson on Wednesday. Okay, guys. So like I say, you pick the side, the more complex side, that's the side that you're going to manipulate. Now, the key or the clue of what we actually need to be doing is in the question. It says, prove the following identity. So we need to think about the identities that we know. Right now, you know the tan identity, and you know the square root of the Pythagoras identity. Obviously, these can be manipulated as you want, but those are the 2 identities that you know. We're going to learn quite a few more this year with the double and compound angles, but right now, that's all you know. When we start to learn more, you can apply other things, but this is what we know. First thing, when proving an identity, the second you see tan, you change it. Okay, unfortunately, tan is a bit of a loner when it comes to the trig ratios. Sine and cos have that co-ratio relationship. We get rid of the tan if we can get rid of the tan. So in my brackets, everything else is the same. This tan squared x is going to become sine squared x over cos squared x. So that's the first thing that I do. Sorry, the pen's gone weird. That's an x. Looks like a weird rabbit thing, but that's an x. Once we've done that, we now have to start thinking about just basic algebra. If you have got a bracket with a coefficient, okay, so here's my coefficient, here's my bracket, algebra tells me to distribute. So that's what I'm going to do. I'm going to leave the 2 there because there's nothing wrong with that 2 right now. Minus cos squared x times 2 is minus 2 cos squared x. And then if you multiply the negative cos x with the fraction, you get a negative sine squared x times cos squared x all over cos squared x. Right. What you can see is that these cos squared x's divide away. And so that last term is actually just a minus sine squared x. Whoops, maybe it would help if I wrote the right thing. Okay, so this is our current situation that we have. Now again, alarm bells. I've got cos squareds, I've got sine squareds, I have a square identity. Now guys, what you also need to remember is that just because I'm about to do it one way, doesn't mean it's the only way to do it. You can change the cos squared x, you could change sine squared x. Both of them are actually going to give you the correct answer. So it doesn't actually matter which identity you choose to change, you will get the correct answer. And if we have a second or two, I might actually just do both so that you can see that there's different ways to do the same thing. All right. So because it's a little bit easier, because if I were to change that cos squared x, I'd have to do some factorization. I'll show you what it would look like in a second. But the sine squared x, because it's just the sine squared x, that's going to be a lot easier to deal with. That's the one I'm going to change. Now, when I say change, what you need to remember, sorry guys, my cat's having noise. Go back down. What you need to remember is the manipulation of your squared identity. So remember, if you want to isolate sine squared theta, it would be 1 minus cos squared theta. If you wanted to isolate cos squared theta, it would be 1 minus sine squared theta. What we want to do is we want to replace the sine squared with the identity. So we've got 2 minus 2 cos squared x minus 1 minus cos squared x. All I have done is I have replaced the sine squared x with the identity. That's it. It means the same thing. But by doing that, I'm now creating a situation whereby everything is a cos or a constant. I can now distribute this -1 into my bracket. So I've got 2 minus 2 cos squared x minus 1 plus cos squared x. And now I collect my like terms. So 2 minus 1 is 1. -2 cos squared x plus cos squared x is a negative cos squared x. And now again, think about the identity. -1 cos squared x is sine squared. And so this whole thing actually just simplifies to sine squared x. Now remember, the whole point was to prove that the left is equal to the right. The left-hand side was sine squared x. So I've proven that the left is equal to the right-hand side. All right, just to show you what I mean, from this step over here, you did not have to change the sine squared x. You could have changed the cos. But in order to do that, you wanted to look like 1 minus cos squared x. So you would have to factorize the first two terms. So we take a 2 out as a common factor, 1 minus cos squared x minus sine squared x. Sorry guys, again, my cat's just causing chaos. Right, so we can do this. And Camilo, I do see your hand. Let me just finish. So we can now take that identity and we can deal with it. So that would mean that we would have 2. Now remember, what's going to happen is that 1 minus cos squared x becomes sine squared x minus sine squared x. Obviously distribute, you've got 2 sine squared x minus sine squared x. And so you get sine squared x. You end up with exactly the same thing. Okay, nothing changes. So that's why I'm saying, sometimes when you look back at memos, they might not have all alternative answers. Just bear in mind that just because yours looks different doesn't mean it's wrong. If you've applied your stuff correctly, you should be good. Most of the time they do give all the alternatives. So you can just you should be able to see what's going on. Okay, so Melo, what's up? Sorry, Camilo. Camilo, you there?
Ma'am, can you hear me? Okay, can you please explain from the part where you distributed after that, the next one, where it's 2 minus 2 cos squared x, from that part there?
So this one over here.
Yes, ma'am.
Okay, perfect. All right, so you're happy with the distribution of the -1?
Yes, ma'am.
Okay, cool. So what I saw was that, hang on, Camilo, let me just make sure. So you're happy that we changed the sine squared x to 1 minus cos squared x, and we distributed the -1 into the bracket. You're happy with that?
Yes, ma'am, I understand that part.
Okay, perfect. So what we're now doing is we're collecting our like terms. So 2 and -1 are both constants. And then we have negative 2 cos squared x plus cos squared x. So those are my like terms that I have. So 2 minus 1 is 1. Negative 2 cos squared x plus cos squared x is negative cos squared x. So I'm just adding and subtracting the like terms, and that's where I ended up with my 1 minus cos squared x, which was that identity that we were looking at earlier. So through adding and subtracting my like terms, I was able to now apply the identity of sine squared x. Does that make a bit more sense?
Yes, ma'am. Thank you.
Okay, perfect. Good. All right, guys, so take your screenshots of this. Woo, so many words coming out of my mouth tonight. And then we're going to have a look at the third type of question, which is looking at a diagram in the Cartesian plane. Kirsten?
Hi, Mom. Can you hear
Kirsten,
me?
are you there? Yes, there we can hear you now.
Okay. Hi, Mom. I just wanted to ask, with these kinds of questions, I never know how to manage my time because it is like you always have to try and get to the answer, and I never know when to change it to a specific identity or when not to. So, do you have any advice?
Okay, you broke up a little bit, but I think I got the gist. If I did not get the gist and I don't actually answer your question, you can shout at me. So, like I said, the first thing I would always advise is if you see a tan, change it. 9 times out of 10, it is not necessary to work with a tan. So if you see the tan, change that to your identity immediately. When it then comes to other identities, you have to look to see what it is you're trying to get your left-hand side or your right-hand side to equal to. Because I knew that I was getting one single term, the sine squared x, because I knew it had to be a single term. I knew that I would have to eventually work with an identity that took multiple terms and condensed it into one term. So that's why I knew I was looking at these. Multiple 2 terms into 1 term. So my advice to my kids whenever we do identities is always keep looking back to what you're trying to prove. I could keep changing sine squared x into multiple different things, but I've reached the point where I've equated it to the right-hand side, so I stop. In terms of your squared identity and when to change, again, I would look and see at what I'm working with. If everything is cos and I've got one sign, change the sign to cos, because then you can start to collect the like terms and so on. In this case, it didn't actually matter. And 9 times out of 10, it doesn't actually matter because the identity all comes from one single equation that is true. So it shouldn't matter. It just means that you might have a more complex working out, changing one of them to another. So my advice, always change tan. And then when it comes to the other stuff, always look back to what you're working towards. And keep in mind, I have to get a sine squared x. What identities involve sine squared x? Do I have those terms in the equation, in the expression that I'm working with to get it to where I need to be?
And then, Ma'am, for the where they say prove the following identity, I always thought that, for example, 2 minus cos squared x brackets, that whole thing in front of the equal sign. So we don't necessarily have to get it to that point. We just have to make sure that our answer is equal to sin squared x.
So technically, that's what I've done. So I've only worked with this left-hand side, but what I've done is I've shown that it's equal to sine squared x. We never work with it as an equation because we don't yet know that it's true. Remember, the question says prove. That means show me that it's equal. So we can't work with it as an equation because we don't actually yet know if it is equal. Now that I've shown that the left-hand side is equal to sine squared x, I could then make the statement of an equation, but I don't actually yet know it because, like you said, the question says prove the identity.
Okay, thank you, Ma'am.
Pleasure. So guys, just on that point that Kristen's just made there, this is why I'm saying you pick a side to work with. So I picked the left-hand side because that was the more complex side. That was the side I could manipulate to eventually show that it is sine squared x. Right now, you've been told to prove it. You don't know that the statement is true. You don't know that the left is equal to the right. Only through manipulation of one of your sides can you show it is the same and therefore say, okay, yes, this is actually a true statement that the left is equal to the right. That's why if you have a look down at the bottom here, my final statement is left-hand side equals right-hand side. I have proven that identity. So you always pick one side to start with, and that's the side you manipulate. If you start looking at past papers, you'll see that they'll say left-hand side, and then they'll manipulate the left, or right-hand side, and they'll manipulate the right. You never work with it as an equation because you're trying to prove it is actually an equation. Okay. Right, I hope you got screenshots. Whew, working up a sweat here. Trig is wild. So let's have a look at the third type of question, which involves the Cartesian plane. Okay, so this one gave me a bit of trouble in the last lesson with my screen, but we're just going to roll with it. Okay, now, guys, this is one that we'll also have a look at again when we start doing our double angles and our compound angles, because double angles is definitely one where we can ask you here and so on. You probably have no idea what I'm talking about when I say double and compound angles. That's fine. We are going to deal with it. Right, but again, if we can do the basics, we can do the harder stuff. So we've been told if sine 12 degrees equals m without the use of a calculator. Now, generally speaking, we always say without the use of a calculator. It's either going to entail special angles or you're going to be able to work it out because you've used your Cartesian plane correctly. Without the use of a calculator, determine the following in terms of. Now, grade 12, this second, you get a question like this, where I give you a ratio and an angle equals m, p, a fraction, whatever. If I give you something like this, my first thing is always draw the diagram. Because remember, what you have been given here is you've been given an angle. So you've been given one of your angles in your triangle. You know that because this is trig, your second angle in your triangle is 90 degrees. And you've been given a ratio. M over 1 is your opposite over hypotenuse of sine. So if we draw our diagram, my diagram's not going to be beautiful, but it's fine. There's my right angle triangle. There's my 12 degrees, because remember, we always measure from the x-axis anti-clockwise. And I can now fill in the information I have. I know the opposite. So there's the opposite. It is m. I know the hypotenuse. It's 1. And using Pythagoras, I can very easily go and work out what my adjacent is. So I'm going to call it x for now. So x squared would be equal to the hypotenuse squared minus the opposite squared. And so when you square root both sides, x is equal to the square root of 1 minus m squared. 1 because 1 squared is 1. So what you actually have is all three sides. Because you've got two of your three angles, you can work out this third angle, and that's 78 degrees. And this is why the diagram is so important. In working out that third angle, you make your life so much easier. You avoid needing to use co-ratios or anything like that. There's no need to use a co-ratio in these situations. If you go and work out all three of your angles, which you will know because you know it's 90 and you've been given one other, you are just making your life so much easier. Now, they don't always say draw a diagram. Often they will say without the use of a calculator and with the aid of a diagram. So they don't always say draw a diagram, but I would always draw a diagram, even if it doesn't say draw it. If they do say with the aid of a diagram, you get marks for your diagram. So put your diagram in so you're not losing marks unnecessarily. Right, but now we've got all of the information we need, we can go and work out what we need to work out. So the first ratio we've been asked for is cos of 12 degrees. Awesome. Here's my 12 degrees. Cos is adjacent, so square root 1 minus m squared over hypotenuse. And so we've got square root 1 minus m squared is the ratio of cos 12. That's it. There is nothing else that you need to do. That is all that is required of you. So when we then get to 3.2, cool. we've got cos of 102. Now, if I look at my triangle, I don't have an angle of 102 there. That's also not possible in a right angle triangle. So now I need to think, okay, I've got an angle of 12. I've got an angle of 78. Could I potentially use a reduction formula to get 102 degrees? Well, yes, I can. Because if I use the reduction of cos 180 minus 78, 180 minus 78 is 102. So now I can apply my reduction formula that says actually what I'm working with is cos of 78 degrees. There's my 78-degree angle there at the top. Cos is adjacent over hypotenuse. So the adjacent here is n. Hypotenuse is 1. So cos of 102 is m. Remember, all of my answers have to be in terms of m. I've got that so far. So now when it comes to 3.3, it's the same thing. I don't have that angle in my triangle. So how can I use a reduction? If I think of this, if I take, I don't know what I'm doing here, sine of 180 plus 12 degrees, that will give me the 192. Now remember your reductions. I didn't really explain it in the last one. You have to think about your quadrants. So 180 plus is quadrant 3. That's where sine is negative. So we're working with negative sine 12. Now remember, you were given positive sine 12 is equal to m. So negative sine 12 is negative m. Or you use your diagram because you have it. So always think back to what information do I have? How did I use it to get the information on my diagram? How am I going to use it to answer the question? Right, when it then comes to question 3.4, we have now got cos of sorry guys. See, this is why I'm saying I didn't explain things. Thank you. See, reduction, 180 minus, quadrant 2, negative. So yes, it should be negative cos. So thank you, negative m. Thanks, Bongi. Clearly, I'm moving too fast for my own brain. Thank you. Right, 3.4, cos of 348. Again, think of your reductions. If we say cos of 360 minus 12, 360 minus 12 is 348. Now, cos in the fourth quadrant is positive, so all I'm actually working with is cos of 12 degrees. You've got your diagram. You can go and work out what cos of 12 is, but you have actually also already answered this question in 3.1. So you automatically know that this is the square root of 1 minus m squared. Okay, now this actually links quite nicely the fact that cos of 348 and cos of 12 are the same thing with the next type of question that we're going to have a look at, which is solving equations. Whenever you are solving a trig equation, remember there are two potential solutions in the first 360 degrees. So any trig equation within the first revolution has two solutions, two positive, two negative. It will obviously depend on the ratio that we're working with. And this illustrates it perfectly. Two different angles, 12 degrees and 348 degrees, gave me exactly the same ratio in the first 360 degrees. And this is what we're going to now focus on when we get to trig equations in the next one. All right, but let's take a screenshot. Obviously, it's not letting me zoom out. So, you know, that's fine. Seems excessive, but anywho. Right, so let's take a screenshot of that. If you have any questions, please let me know. Otherwise, we're going to have a look at some equations. I don't think we'll get through all of them, but we will get through the first two, which will show you just the basics of trig equations, but then also how we solve more complex trig equations, which again, really important to know. And then again, guys, I will put up some grade 11 revision of trig so that you can practice this. I will do my absolute best to do it before Wednesday's lesson, but if I haven't done it by Wednesday, you just need to remind me. Okay. Alrighty, so let's have a look at the fourth type of question. So the fourth type of question is solving a trig equation. No, so sorry, I wanted to make it bigger. It's solving a trig equation. Now, there are 4 basic steps that I would suggest following if you want to solve a trig equation. And when I say basic steps, I mean in general. If you can do this, you should be okay. So the first thing that we want to do when we solve a trig equation, I'm just going to write it on the side for us. Okay, apparently I'm not going to write it there or there. There we go. Is we want to isolate the trig ratio. So when we look at question 2, that'll become a bit more important. Right now in question 1, my trig ratio is isolated. So step 1 is done, I don't need to stress. Step number 2 is to then determine my reference angle. Now there are a few different ways that you can solve trig equations. Some people use reference angles, some people don't. I never used to use a reference angle, but I am also aware of the fact that it is the most commonly used method, so I have adapted, but it's not the only way to do it. Now, when you determine your reference angle, you ignore the sign of your ratio. So as I explain these questions, I'll explain what I mean by that. Once you've got your reference angle, the third thing that you want to do is you want to use the sign of your ratio. So we ignored it when we did the reference angle, but now we use it to determine which quadrants we're working in. And it's important to determine the quadrant we're working in because we need to know what reduction formula we're working with. And once we have done that, we are able to go and solve for our unknown. Right, so if you can remember those 4 basic steps, you should be good. So we're going to start with question A, which is a nice, easy, straightforward, nothing complicated. You did this in grade 10 when you first started trig equations. So the first thing we do is isolate the trig ratio. That's already done for me. So the next thing that I need to do is I need to work out my reference angle. I'm sorry about the writing. I don't know what's happening. We're just going to roll with it. So, okay, let's go down here. So my reference angle. We ignore the sign of the ratio. So this is a positive 0.32, but I ignore that. I'm going to type into my calculator shift sign. So it'll give us sine -1, and I type in the 0.32. Whatever that gives me is my reference angle. So this would be 18,662, and there's a whole bunch of decimals. That is my reference angle. I now use the sign of my original ratio, which in this case was positive, to determine my quadrants. Now, sine is positive in quadrant 1 and quadrant 2. This tells me the reduction to use, theta and 180 minus theta. So what we then do is we take the angle that we were given, so in this case it's just x, and we now solve for these 2 different quadrants. Don't know if that's going to fit either, but we're going to work with it. So x is equal to, quadrant 1 is just theta, so just 18,66 degrees. Now, guys, remember this is a trig equation. You have got multiple solutions every 360 degrees. So we have to remember to say plus k times 360, where k is an integer. Okay, that's not going to work, so I'm just going to write it down here. Where k is an integer. K as an integer is important because you can add 360 or subtract 360 as many times as you want, you still end up in the same place. So that's my first solution. Please do remember your k times 360 and k as an integer. You will be marked down if you don't have it. Right, in quadrant 2, so again, we take the angle, which in this case is just x, is equal to, and now we apply our reduction, 180 minus my reference angle of 18,66, so on degrees. Okay, this is the second solution for my trig equation here. So 180 minus that gives me x is equal to 161,34 degrees plus k times 360. K is an integer. Now, once you've written integer once, you don't need to write it again. I always put it in my final answer again, just because it's your final answer. You should have all the information in it. But you need to have the plus k times 360 every step. Okay, so that's the basic trig equation. We can do that, we're okay. So if we now have a look at the second question, this is a lot more complicated because there's a lot more going on. And this is sort of the one that we need to be comfortable with. So the first step is isolate the trig equation. And guys, the trig equation is the cos of the angle, or the sine of the angle, or the tan of the angle. So what that means is I need to get rid of that coefficient 3. To get rid of it, I would divide both sides by 3. So that means I've got cos, this is step 1, of 2x plus 10 degrees is equal to negative 0,8 over 3. If you want to actually write that as negative 4 over 15, you can write it as that if you want. It is completely up to you. Siva, I'm going to be honest, I don't know what you mean part 1 or part 2 of trig. It's general trig. I don't know if that helps. You get general trig, you get trig and triangles where you use your sine rule, your cos rule, and your area rule, and you get trig graphs. So this is general trig. I would assume probably part 1, if I just make an assumption here, that this is just general trig that we're talking about. Okay, so guys, I've isolated my trig ratio, and I need my reference angle. So remember, we ignore the signs. We're going to say shift cos, so cos negative 1 of, I'm not going to type in negative. I'm just going to type in 0,8 over 3, and I get my reference angle. So here, the reference angle is equal to 74,53, and there's a whole bunch of decimals. Now I use my sign to determine the quadrants. Cos is a negative ratio here. So cos is negative in quadrant 2 and quadrant 3, which means I'm using the reduction 180 minus theta and 180 plus theta. That's where my sign becomes important. Now I'm actually going to go and solve. So remember, you take the angle you were working with, in this case 2x plus 10, and that's what you equate to your reduction. So in quadrant 2, I have got 2x plus 10 is equal to my reduction, 180 minus my reference angle of 74,53, blah, 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 plus k times 360. K is an integer. Now I go and solve. So 2x plus 10 is equal to 180 minus that whole thing, gives me 105,46, whole bunch of decimals, plus k times 360. I'm going to subtract 10 on both sides, giving me 95,46, blah, 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 bunch of decimals, plus k times 360. And now this is where things are really important, grade 12s. In order to get rid of this coefficient of 2, you have to divide every single term by 2. And so that means that this k times 360 becomes k times 180. So x is equal to 47,73 plus k times 180, where k is an integer, and you've solved for x. Now, guys, that coefficient to x is really important. Remember, what that does is it changes the period. So if that coefficient is 2, 3, 4, whatever, what actually ends up happening is your graph actually happens much quicker. The cycle of your graph is much faster, which is why the period changes to 180. Right, if I go over to quadrant 3, remember you take the angle that you're working with, 2x plus 10 is equal to the reduction, so 180 plus my 74,53, blah, blah, blah. And you solve again. Now, obviously, guys, if you can do everything in, like, if you can shorten your steps, fine. 180 plus 74, blah, blah, is 254,53, and there's a bunch of decimals. K times 360. Subtract 10 on both sides. 2x is equal to 244,53, so on, plus k times 360. Now again, you're going to divide everything by 2, so x is equal to 122,27 plus k times 180. So this is definitely a more complex type of trig equation because you have so much going on. but this essentially covers all bases. It covers what to do with the coefficient. It covers what to do if you've got a coefficient to your angle x. So here we have 2. Covers if you've got plus or minus. If you can, again, whoopsie daisies, follow these 4 steps, in general, you should be able to solve a trig equation. Alrighty, so I'm going to let you take a screenshot there. I'm fully aware of the fact that I have spoken for pretty much an hour straight.